Right now, 15 billion miles from where you are sitting, a machine older than the internet is running out of power. And in the next few weeks, NASA is going to do something to it that has never been attempted before at this distance, on hardware this old, with a communication delay this long. They are calling it the Big Bang. Not because anything explodes, because everything changes at once. This is not a metaphor, not a dramatic exaggeration added for effect. Not a worst-case scenario dreamed up to make headlines. It is the actual, official, on-the-record plan for what NASA engineers are attempting on Voyager 1 in July of 2026, right now, as you're watching this. And there is no backup plan. There is no second attempt if it goes wrong. Because if it goes wrong, Voyager 1 does not get a chance to try again. Stay with me, because to understand how a 49-year-old spacecraft ended up here, on the edge of a single all-or-nothing gamble, you need to understand what has already been sacrificed to get it this far. Voyager 1 launched on September 5th, 1977 from Cape Canaveral. A machine roughly the size of a small car, weighing about 1,800 pounds, carrying 10 scientific instruments and a mission that was supposed to last 5 years. Fly past Jupiter, fly past Saturn, send back some pictures, go quiet. That was the plan. It has been operating for 49 years. It is currently the most distant human-made object in existence, over 15 billion miles from Earth, deep in interstellar space, beyond the boundary where the sun's influence ends and the space between stars begins. Of the 10 instruments it launched with, 7 have already been shut down. Not because they failed, because there was no longer enough power to run them. On April 17, 2026, NASA sent a command across that 15 billion mile gap. 23 hours later, the signal reached the spacecraft. 3 hours after that, the low-energy charged particles experiment, an instrument that had operated almost without interruption since 1977, went dark. On purpose, by choice, because the alternative was worse. Here's the part almost nobody outside the mission team is talking about. That shutdown was not simply the next scheduled step in a long, carefully planned retirement. It was triggered by something that nearly ended the mission months earlier. In late February 2026, during a routine maneuver to roll the spacecraft, Voyager 1's power draw spiked unexpectedly, close enough to the edge that it nearly triggered the spacecraft's automatic undervoltage fault protection. A self-preservation system built into the spacecraft's oldest programming, designed to shut down non-essential systems the instant the power supply looks unstable. Think about what that actually means. A machine built in the 1970s, using hardware simpler than a modern calculator, came within a hair's width of triggering its own emergency shutdown protocol, 15 billion miles from anyone who could help it. If that protection had activated, recovering from it would have meant a multi-day process of diagnosis and repair, conducted entirely through 23-hour one-way commands, with no guarantee of success. NASA's engineers looked at that near miss and made a decision. Shut down the LECP now, on their own terms, before the spacecraft's own safety systems made the choice for them in a way nobody could control. Voyager 1 now has 2 functioning science instruments left. A magnetometer, measuring the magnetic fields of interstellar space, and a plasma wave subsystem, listening to the charged particles drifting through the void between stars. That's it. 2 instruments, out of the original 10, still reporting back from a region of the universe no other human-made object has ever reached. And here's the number underneath all of it. Voyager 1's power comes from radioisotope thermoelectric generators, essentially containers of decaying plutonium-238, converting heat into electricity. That power source loses roughly 4 watts every single year. Not 4%, 4 watts permanently forever, with no way to add more. The math is not complicated, and it is not forgiving. Every year there is less power. Every year, something else has to go dark. Kareem Badaruddin, the Voyager mission manager at JPL, said something about the LECP decision that captures exactly what this mission has become. He said shutting down a science instrument is not anyone's preference, but it's the best option available. That is not a scientist celebrating a discovery. That is an engineer making peace with loss over and over again, one instrument at a time, for years. But here is where the story turns. Because the team did not shut down the LECP completely. They left a single half-watt motor inside it, still powered, still warm, still technically alive. Not because it does anything useful right now, because if the Big Bang works, they want the option of turning the LECP back on. So what actually is the Big Bang? It is not a new instrument. It is not a repair mission because there is no such thing as a repair mission 15 billion miles from Earth. It is a complete restructuring of how power flows through the spacecraft, swapping a group of powered systems out all at once for lower power alternatives, redistributing every remaining watt to squeeze more operational life out of hardware that has already outlived its design by nearly 10 times over. The reason it has to happen all at once, instead of gradually, one careful step at a time, is about what happens in between. During any reconfiguration like this, there are moments where the system is neither in its old state nor its new one. Those in-between moments are dangerous. They can trigger the exact same fault protection system that nearly activated in February. The entire philosophy behind the Big Bang is to move through that danger zone as fast as possible, all at once, rather than lingering in an unstable configuration, one change at a time. NASA tested this procedure first on Voyager 2, not because Voyager 2 matters less, because it currently has slightly more power in reserve and sits a little closer to Earth, making it the safer place to find out if this works at all. Those tests ran through May and June of 2026. And now in July, if those tests went well, the same procedure gets attempted on Voyager 1 itself. The riskier spacecraft, the one with less margin for error, the one where a mistake means losing the two instruments that are still working. Every single command in this process has to travel 23 hours to reach the spacecraft, and whatever Voyager 1 does in response takes another 23 hours to come back. That is not a typo. That is not dramatic license. Nearly 2 full days pass between sending an instruction and finding out what happened. There is no way to intervene in the middle. There is no way to stop it halfway through if something starts going wrong. Once the commands are sent, the outcome is already decided, and the team simply has to wait to find out what that outcome was. Matt Hill, the principal investigator for the LECP instrument at Johns Hopkins Applied Physics Laboratory, described what that instrument had actually given us over nearly 5 decades. Its measurements were part of how scientists first sensed the moment Voyager crossed out of the solar system entirely. That is what is sitting on the table right now, waiting to find out if it gets a second chance. If the Big Bang succeeds, the power savings could extend the operational life of both spacecraft's remaining instruments well into the 2030s. And there is a real, specific possibility that the LECP, the instrument shut down in April, the one with a single half-watt motor still quietly warm inside a dark chassis, gets switched back on. If it fails, there's no version of this story where NASA simply tries again next month. The margin does not exist for a second attempt. Whatever state the spacecraft ends up in after the reconfiguration is the state it stays in, possibly for the rest of its operational life. And all of this is happening on a clock that keeps moving regardless of the outcome. In November of 2026, Voyager 1 will cross a distance of roughly 16.1 billion miles from Earth, becoming the first human-made object to sit a full light day away. At that point, the signal sent from Earth will take a complete 24 hours just to arrive, and the reply will take another 24 hours to come home. 2 full days for a single exchange of information, with a spacecraft that by then may be running on whatever configuration the Big Bang left it in. Now step back for a second, because there's something underneath the engineering that's easy to miss if you're only counting watts and instruments. The people making these decisions are not the same engineers who built this spacecraft in 1977. Most of them have retired. Most of them are gone. The team at JPL keeping Voyager 1 alive today had to learn the design philosophy of an era before their own careers began, just to speak the spacecraft's language well enough to keep it breathing. Every command they send is written in a dialect of engineering that barely exists anywhere else in the world anymore. And every one of them knows that the choices they make this month could either buy Voyager 1 another decade or end its 49-year mission in the space of a single 23-hour transmission. This is what makes the Big Bang different from every other moment in this spacecraft's long, improbable survival. It has cheated silence before. It came back from months of transmitting unreadable gibberish in 2023 after a single memory chip failed, brought back online through patient months of remote diagnosis across a 44-hour round-trip delay. It has already outlived every prediction made about it in 1977, but every one of those recoveries happened gradually, one careful step verified before the next. The Big Bang is different. It is not gradual. It is not reversible mid-process. It is everything at once, with the outcome locked in the moment the last command leaves Earth. Somewhere in the coming weeks, that outcome will already have happened. The commands will have been sent. The spacecraft, 15 billion miles away, will have already responded one way or another, its new configuration already either holding steady or already failing, hours or days before anyone on Earth even knows which. We are, right now, in the waiting. And that waiting is the story. Not because we don't know the ending yet, because the ending is already written somewhere in the dark, moving toward us at the speed of light. And there's nothing left to do but listen for it. Voyager 1 was never supposed to still be here. 5 years, then silence. That was the plan in 1977. Instead, it has spent 49 years refusing to stop, shedding instruments one at a time like a traveler lightening their pack for a journey with no end in sight, still sending its signal home across a gap that keeps growing every single day. The Big Bang is the next chapter in that refusal. One roll of the dice sent 15 billion miles into the dark, with an answer already decided and simply not yet heard. If you want to know the moment NASA confirms whether the Big Bang worked on Voyager 1, subscribe right now and turn on notifications. Because when that signal finally arrives, we're covering it here first, with the real data, the actual numbers, and nothing invented that the instruments didn't measure. The commands are already on their way. The answer is already sitting somewhere in the space between here and a spacecraft older than most of the people trying to save it. We are still waiting for it to arrive.